Hello everyone, this is Chang-Hoon Kim from the Pattern Recognition Lab of Friedrich Alexander University Erlangen-Nuremberg in Germany. So it's an honor to be here. Today I'm presenting about our work, physics-informed graph neural network for medium high voltage AC power flow with edge-aware attention and line search correction operator. So this talk is basically about how to improve vanilla GNN with a task-specific structure for a certain domain, which is here, electrical power system. So let me first introduce the problem behind this work, AC power flow. So the recent German grid, the penetration of renewable energies and various types of electrical consumer cause grid congestion. And this grid congestion is mainly due to the voltage limit violation across all the electrical nodes. So to detect and relieve it, the grid operator needs to solve thousands of AC power flow scenarios in few seconds. That's the reason the speed of the AC power flow solver is very important. However, the speed is only useful when the solver's predictions stay physically grounded. So and then now I will formulate the AC power flow problem as a graph problem. So as you can see here, the nodes are one of those type select generated load. And the edge is the transmission line with line parameters. And the nodes features are P, Q, V, theta, which are active reactive power and voltage magnitude and voltage angle. So here, the goal of AC power flow is to find the unknown node voltage state across all the nodes by solving AC power flow equations PQ in terms of V, theta, and admittance features. Since these AC power flow equations are nonlinear and underdetermined equations, we need to use Newton-Raphson solver or graph neural solver, which replace the Jacobian matrix into simpler graph neural network. There are limitations of Newton-Raphson solver as well as graph neural network-based solver. First, the Newton-Raphson is an iterative method, which is highly accurate but very slow. This is due to the Jacobian computation and its inverse computation by sparse factorization, which is not GPU friendly. Second, the graph neural network-based solver, which uses the supervised loss as a training loss, is fast enough because it can utilize the GPU computation power, but it requires the training samples labeled by Newton-Raphson. And the physics equations are incorporated neither through the model structure nor through the training loss function. Third, the recent paradigm physics-informed graph neural network somehow solved this problem. But it has still limited structure awareness, and there is no mechanism that guarantees the physically plausible behavior at inference. So this leads to our research question that can we design a more trustworthy physics-informed graph neural network solver with greater structure awareness and an inference time correctable mechanism? So we found two main gaps in the previous method. First is the representation gap, and second is the inference gap. The representation gap is caused by the uniform message aggregation through the multi-layer perceptron. And second, the inference gap is caused by the inoperative physics loss at inference, since the physics-informed enters only through the training objective as a regularizer. So to close these both gaps, we designed our method pipeline with two main components. First, for the representation gap, we designed a transformer-style and edge-aware attention-based message aggregator instead of using multi-layer perceptron-style uniform message aggregator. And second, for the inference gap, we designed a backtracking line search-based inference time correction operator, instead of directly accepting the message and voltage setter update proposal based on the aggregated message. So I will take a closer look on these two main components on the next slide. So in the edge-aware rotation, the query is the projection of target node ice features, while the key end values are the projection of neighboring node J's features. And in the scale dot product attention, we add an edge bias based on the line parameters. So it makes the edge conditioned attention score where it moves from an isotropic graph filter to an anisotropic graph filter, which means that it can model the neighboring nodes effect differently. And more importantly, this edge-aware attention works as a fully differentiable non-operator layer inside the computational graph by injecting the edge coupling explicitly in the forward path, unlike the NLP style message aggregation where it is only implicit through the node features. And to restore the inoperative decrease criterion at inference, we apply backtracking line search at each message passing update step k. First, we design a Mori function as an infinity norm of PQ residue, active reactive power residue across all over the grid. And we initialize the step size alpha to 1 and take the step and check whether the Mori function value is decreased enough. If not, we backtrack one step before and check again whether this reduced step size low alpha decrease the Mori function value sufficiently. So we repeat until the decrease criterion is met. And then by doing so, we can compensate the inoperative physics loss during inference, resulting in a more stable and physically plausible behavior at inference. And this is the visualization of 3D space of Mori function, how each message passing step k is corrected by line search operator. As you can see, we try few steps and reduce the step size, and it eventually go through the minimum of Mori function by iterating each message passing step k. Yeah, so we reach at the minimum point. And for the experiment, for the data, we generate the diverse grid scenario based on the European German-inspired medium-high voltage parameter range for both node features and edge features. After removing some outliers, we attained about 30,000 of medium-high voltage scenarios, and the grid size is from 4 to 32 with various topology. And for the training, we only used physics-informed loss discounted over message passing step k without using any supervised loss based on the Newton-Raphson layer. And we used Adam W optimizer and cosine learning length scheduler for the training. And the split training validity test split was equally splitted as we can generate the synthetic data based on the given parameters. And we used the machine RTX 3070 with i7 20-core CPUs. And for the batching strategy, we used block diagonal batching rather than same-size batching. And for the evaluation, we only used the Newton-Raphson solution as a reference state to compare our physics-informed graph neural network solver against the Newton-Raphson. And then we reported voltage RMSE and angle RMSE against the Newton-Raphson solution. And we also compared the throughput of our graph neural network solver with this both scenario regime, single case and multi-scenario. So this is the main result with ablation study. Here, the ablation mainly compares two things. First, the effect of the message aggregation, and second, the effect of the inference correction mechanism. So for the message aggregation, MLP versus edge-aware style message aggregation. So overall, the attention-based message aggregation performs better than multi-layer perceptron style message aggregation. And this again is especially clear in the medium voltage where the grid is more anisotropic. And second, we also found the inference time correction mechanism constantly improved the result in most of the cases. For example, in high voltage scenarios, the full model with attention-based message aggregation with two inference time correction mechanism, voltage update caps and line search correction operator performs the best. And in the medium voltage, the variant without voltage update caps performs slightly better. And for the combined voltage data set, again, the full model with attention aggregator and voltage update caps and line search correction operator performs the best. So here the main takeaway is the attention improves the representation of graph neural network solver, and the line search drives the robustness in the inference. So our physics-informed graph neural network achieves 3.3 e to the minus 4 voltage magnitude RMSE and 0.08 angle RMSE against compared to our Newton-Raphson solver, which is minus 96% lower and 88% lower than the Newton-Raphson solver. And for the throughput, we compared our physics-informed graph neural network implemented as PyTorch against the Newton-Raphson, coded as a vectorized and optimized NumPy solver. And we reported the median inference time over multiple runs with 2 warm-ups and 5 repeat cycles. And as you can see here, in both scenario regimes, the Newton-Raphson builds superlinearly but polynomially. So in single scenario regime, the Newton-Raphson stays competitive when the grid size is small, but the physics-informed graph neural network solver becomes faster as the grid size is increasing. In the multi-scenario regime, our physics-informed graph neural network solver constantly outperforms the Newton-Raphson. So we can conclude our work by revisiting two main priors we have addressed. First, for the representation level, the edge-aware based attention message aggregation provides the line physics directly into the message aggregation, making the fully differentiable non-operator layer inside the computational graph, while capturing the grid's anisotropy more faithfully. And in the inference level, our backtracking line search-based inference time correction mechanism restores the inoperative physics decrease criterion at inference, resulting in more stable and physically ordered behavior. So basically our method, physics-informed graph neural network with edge-aware attention and line search correction operator, achieves the Newton-Raphson level accuracy while retaining substantial throughput advantages. So this work highlights the promise of graph representation learning in power system sector, motivating future research with rigorous benchmarking and broader scalability and integration into real operational grid. Okay, thank you very much. If you have any question, I'm happy to discuss. Yeah, yes, please.
Go ahead.
Maybe mic would be better to communicate.
nice talk.
Thank you.
So in your physics-aware representation,
Yep.
are you essentially using graph attention network?
It's different with graph attention network because GAT style is using additive aggregation instead of attention-based transformer style aggregation. So it's a little bit different with GAT style because the aggregation is based on the edge-aware attention with the explicitly adding the line parameters.
But GAT also allows you to have edge features, right?
Mm-hmm.
Is there any special reason why you have this FLIJ term that's added, like a bias there? I mean, my question is basically why not GAT with edge features?
Mm-hmm. So it, yeah, probably essentially the similar and same idea, but also the difference, as I understood, is the GAT is using only the additive method, but here we design the transformer style message aggregation. Like the QA is the target node i's feature, and while the key and values are neighboring node j's feature. So it's very the same idea with the transformer in the legacy model, but as I understood, this is the first approach that we apply in the power grid, the graph neural network in this transformer style. And
One
this,
more question.
yep.
So in your line tracking?
Yeah, line search correction operator, exactly.
Yeah. So there you're using this power flow equation, right?
Power flow equation, exactly.
The various function, the power flow equation is kind of included, right?
Yeah, exactly.
So this is like you have to know global state of the graph to update locally, right?
So the multifunction is a simpler version of power flow equation, which just take the infinity norm of entire nodes. So it takes just maximum node features, not seeing every nodes in the grid. So it's very lightweight inference time correction mechanism. So the physics equations incorporate into the training loss function with the physics informed loss. But in the line search, we somehow want to compensate this inoperative physics loss during inference. That's the reason we just bring the lightweight line search correction mechanism, which is inspired by just gradient descent mechanism we are usually use, but this is just applied for this message passing step K.
But when you change the local parameters, right, that through the power flow equation, every variables are coupled, right? So when you make a local change, it will affect other delta P, delta Qs, right?
Yeah.
So that's taken into account into the merit function, right? When you take the maximum, you have to account for the changes in other nodes, not your local node that you're updating.
Yeah, so currently I'm just considering the maximum of the infinite norm of PQ, but it's like complexity and speed trade-off. If we can include the local like features as well in the inference time correction mechanism, it definitely improved the performance, but could decrease the speed. Yeah, but yeah, thank you very much.
Thanks everybody. Thanks for attending this very nice session. Let's thank the speaker again.
Thank you very much.